Hey guys, and welcome to the next set of notes from topic 5, which is going to be on phase changes and latent heat. So we're going to talk about the energy and phase changes, and also what changes go about when the temperature changes in a substance. Okay, so the first thing I want to talk about is a change of phase or change of state of matter. Okay, so obviously the three states of matter: gas, liquid, solid. Okay, and you guys know to get certain ones, you either got to gain energy or lose energy. Some of those are colder for a certain substance. For an example, ice. Ice is cold. Water's kind of in between, and gas is super hot, depending. So that's pretty much with the phases. Now, latent heat is the heat required for a phase change to take place. So obviously for different substances, this is going to vary a little bit. Some will actually boil pretty easily, and some will not. Okay, the amount of heat required for different substances varies. So as I mentioned, so different substances will have different melting and freezing points, as an example, or boiling points in that matter. Heat is measured in joules or calories. So in other countries, they use joules typically. In science, calories, you guys know, you've heard that with food. So calories actually the amount of energy that we gain from eating certain foods. And obviously if you overdo it, it's not good. So you don't want too much energy, and then because that will get stored as fat in your body. All right, so here are the phase changes. So solid to liquid water is melting. Okay, and obviously the ones going to the right, they're in red. Energy is being absorbed. So to melt ice, you know you have to add heat, and it's 334 joules per gram that we're adding. Then when we get to liquid water, to evaporate it, it's actually a lot more energy. It's 2,260 joules per gram. So evaporation is a lot harder to happen than to melt the substance. That's why it will take days for puddles sometimes to disappear in the ground. But ice, on the other hand, can melt pretty quickly, all right, within hours. So evaporation, a lot of energy required for that to go on. Now to go in the reverse, we release energy. So condensation, all right. So you guys know in the morning you wake up, the grass is wet. The reason why it's wet, because it cooled down overnight. And the cooling process, then water droplets actually form on the grass. So that's condensation. Also, clouds form by a cooling process as well as air rise expands. Right? We're going to talk about that in the coming chapters. And freezing, on the other hand, is also release of energy. So when you put something in a freezer, a lot of times it's actually quite warmer than what's in the freezer. So to actually freeze something, you have to remove the energy from that object. And that's why the back of a freezer will also give off heat. All right, because in the coils, they're actually removing the heat that's within the freezer and releasing it. Okay, this diagram I'm going to go over in a few minutes on a piece of paper with you. I'm going to redraw it and explain it. But this is the phase changes for latent heat, and also the time in which these phase changes occur is shown on this diagram as well. Okay, melting is when solid goes to a liquid, so energy is gained, as I mentioned. Freezing, on the other hand, is liquid to a solid, energy being released. And the heat involved with these phase changes, the 334 joules per gram, like I mentioned, either released or gained, is called heat of fusion. So this is a special term or special name for those phase changes. Okay, and then the reverse, so vaporization, liquid to a gas, energy gain. Condensation, gas to a liquid, energy loss. This is called the heat of vaporization. And again, that's 2,260 joules per gram. The front of the reference table shows these numbers, so you don't need to memorize them. So you can look them up and learn whether or not the phase change requires energy to be gained or lost. In vaporization, just so you guys know, that's the general term for turning into a gas. You guys know evaporation, that's used for water only typically, because that happens at normal room temperature or just normal temperature conditions. evaporation. Okay, and sublimation is an interesting one. This is a solid changing right into a gas, skipping the liquid phase. So dry ice, which you guys may be familiar with, in the bottom of freezers. Typically in stores, you'll see chunks of this in case they do lose power in the store, to keep the food cold for many hours beyond if they do have a power outage. So CO2 solid, and it changes right into a gas. It skips the liquid phase. Really neat stuff. Omaha Steaks, that's a company that actually ships using that. Sometimes chocolate companies, when they're shipping chocolates in the mail, will actually put dry ice in there to keep it cold so it doesn't melt. All right, and there is a little video which I will post for you guys showing a little experiment you can do with dry ice, which is really cool. So basically, heat is gained during melting and evaporation. Heat is lost during freezing and condensation. And more heat is needed for vaporization than melting, and more heat is lost in condensation than freezing. Okay, and temperature remains constant during a phase change because all the energy is used in the phase change. So, great example of this, guys. Just so you know, the reason why you put ice in your iced tea or any drink is to keep the temperature close to 0 degrees Celsius or 32 degrees Fahrenheit, because the temperature will not change. Sorry about that. Get that out of the way. Will not change during that phase change while it's melting the ice. Okay, so it will stay constant. All right, so just quickly, I want to go through the graph that you guys saw earlier. So let me switch to my camera. Okay, so the graph you saw earlier. Okay, so if we start out with a solid substance like ice, so this will be the phase changes of water, basically. And this will be graphed out. So if I started out with a chunk of ice, and actually you can lower its temperature below freezing if you actually add salt. That's a little trick we do. And you start at -10, start heating it up. The ice will actually get closer to the 0. Once it reaches 0, we call this the melting point. Obviously, if you're going the other direction, it is then called the freezing point. So some people will use those terms interchangeably because they are the same temperature, melting, freezing point. Okay, then you're going to start melting the ice. Okay, so it starts out as a solid here. And when you melt the ice, the temperature will stay constant. That's why we put ice in our drinks, to keep the temperature constant in our drink. So melting, as I go this way, and then as the temperature begins, after it finishes melting the ice 100%, now you just have water. Now the temperature of the drink will now rise. Okay, and it will rise, rise, rise. And if you were heating it up on a stove, you would reach eventually a temperature right here. This is called the boiling point. Okay, obviously you guys know it will start boiling and you'll get the bubbling going on. It will stay at 100 degrees Celsius while it's boiling. Okay, and it will stay constant until it gets to the point where all the gas is now gone up and so all the liquid has changed into a gas. Okay, and now it's a gas. So if you label all the parts of this, so gas, liquid, and this will be evaporation or vaporization. Okay, so solid, liquid, gas, those are the phases of matter. During the phase of the matter, their temperature is changing. During the phase change, though, melting, vaporization, it stays the same. And then you could do the same graph in reverse. Start as a gas, cool it down, and then you go this way. This would be condensation. Okay, then a liquid, and then obviously freezing when you go back to a solid. So you can do the same graph in opposite direction also. So that's a latent heat graph. And this sort of thing you'll see in some of the questions in the chapter, so I just want to point it out to you. Also note it on the bottom here, I wrote time in minutes. So melting takes a lot shorter time than vaporization, as I'm showing in there. Also to note, steeper slope here, so the rate of temperature change as a solid is greater than liquid and gas. Okay, so those are just little things you'll notice with the graph. All right, so hopefully you guys enjoyed, and that's pretty much that topic. Thanks.